Check, check.
Yeah, I need it.
Okay.
Hi. Good morning, everyone. Thanks for being here. I know it's early. It's the third day. You might be tired, but this is going to be awesome. So congratulations for having come. Just one single thing. We're going to show live code, and I went that way, and it's a little bit blurry if you're sitting in the back. So please try to sit in front, because we're really going to code, and you would probably like to see the code. So you will want to be closer to the screen. Or not, it's up to you. So, hi, I'm Esther de Nicolas. I work in the AI marketing team. This is Kim Lang. He's a researcher in the cryptography group at Microsoft Research. We're going to do a deep dive into homomorphic encryption. And when I say deep, it's going to be way deeper than what we did in the session and what we've been doing at the booth. We're going to really show you how to implement this. And for those of you that haven't gone through through our booth or through one of our other sessions, homomorphic encryption is a new encryption scheme that what basically allows you is to compute over encrypted data. And this is important in the sense of AI, because one of the challenges that we have when we're implementing AI is to actually get the trust of customers to provide data to an external provider to compute over that data. But with this new approach, we can compute over encrypted data, so there's no need for the user to expose any kind of data to us. So that's, I mean, it's really a new type of consideration when it comes to cloud services, not only AI, but cloud services in general. And this is really interesting. So that's why I wanted to have Kim Laina, who is the researcher, one of the researchers working on this, because we've been doing a great amount of breakthroughs in the last years, from being the first ones to actually prove that this worked on deep learning algorithms, to getting some performance improvements that now is making this technology to be real and to be applicable in a lot of different scenarios. So we're really excited to share this with you. It's open source, so you'll be free to try it out today. And I will be around going with a mic. This is meant to be a very interactive session. So I'm just handing it over to Kim. And if there's any questions and at any point of the presentation, just raise your hand. I will go to where you are, give you the mic, and please feel free to ask any question at any time. So thank you, Kim.
Excellent. Thank you, Esther. So, well, you already kind of explained a little bit what homomorphic encryption is, and indeed, it is a new type of encryption technique. It's different from these traditional systems like AES and RSA that you might be familiar with. And the notable difference is that homomorphic encryption allows you to compute on encrypted data. So you don't need any key or anything like that to first decrypt and then compute. You can compute directly. Homomorphic encryption is actually also quantum secure. So even if there were quantum computers that can break these traditional schemes like RSA and some elliptic curve schemes, homomorphic encryption uses types of hard problems that are not vulnerable to quantum attacks, if that is a significant consideration to you. Here's a little schematic showing again this interaction model and how we're thinking about this. So we have a customer and we have a cloud service provider, and there's a privacy barrier between these two, meaning the customer doesn't want to share their data. Customer can, or a client device, this could be a mobile phone, laptop, it could be another company. They have some files, and they choose a key, and they encrypt these files. And because it's encrypted, they can get long-term cloud storage. This is kind of standard. It's not hard to get the encrypted cloud storage. However, because this is homomorphic encryption, we can apply computations here in the cloud services side. And basically, if you have very good eyes, you can see that the color of the file has slightly changed. It's my indication of some kind of computation being done on this encrypted data. But here, Azure doesn't have any keys to decrypt this. The result can be sent back to the customer, who can remove the encryption with their key. Now, why am I talking about this? I'm talking about this because we're doing a tremendous amount of research in homomorphic encryption, both in the deeply theoretical aspects, but also implementation. We have developed, since 2015, in fact, a library called Microsoft Seal. So it's a C++ library and it has .NET standard wrappers. It's actively developed today, and it's available open source, so anyone is welcome to download it and use it and even contribute to it. So we do take also pull requests and all that good stuff. Seal works on Windows, Linux, and Mac, all basically equally well. In the future, well, the public version of Seal only is designed for running on CPUs, but we have already looked at GPU and FPGA acceleration, and in the future, this is going to be a very important trend in this technology. So let's talk about performance. If you've heard about homomorphic encryption before, you've probably heard that it's very complicated, mathematical, very slow, and it probably was true when you heard it, but the situation has changed a lot, and this is what I'm trying to communicate in this slide. So here we have the performance overhead on the y-axis, and on the x-axis we have the year. This is a very recent technology. Homomorphic encryption was invented only in 2009, and at that time, you can see that the performance overhead was, kind of significant, 12 orders of magnitude. It means that basically you can't do anything. At that time, you couldn't do anything. It was only a theoretical tool for theoretical cryptographers. But going forward to, say, 2015, you can see that on this logarithmic scale, we've come down to to halfway. So that's pretty good. That's like amazing improvement. Several orders of magnitude improvement. Going forward to 2017, the capabilities of homomorphic encryption have changed radically. We've come up with new schemes that have new kinds of capabilities. The performance has improved even more. Now we're looking at something like 3 to 4 orders of magnitude, which is still like very significant, of course. Going forward, like I said, we're looking at hardware acceleration here, and we predict that we're going to get some further 2 or so orders of magnitude improvement from this. And past 2021, it's kind of hard to predict what's going to happen. Now, of course, you do see that still we're talking about a substantial overhead here. This means that this is not a generic technology that you can just throw at some big data. It doesn't work that way. This is a technology where you have to think about very carefully about what you're doing. You have to apply it to reasonably sized or appropriate sized data and appropriate type of computations. It's a non-generic technology. So here's a little table showing concrete performance numbers, and it's a little bit confusing, so I'm going to take some time to explain this. And this will also explain a little bit about how homomorphic encryption works. These experiments are done on some basic desktop machine on a single thread. Seal supports 2 encryption schemes. Both of them are homomorphic encryption schemes. And these experiments are done using a scheme called CKKS. It comes from the names of the authors. Now, what do we have here? The very first column is labeled polymodulus degree. So this is actually one of the parameters. When you set up the encryption scheme, it's one of the parameters in that like describe how the scheme is working. And you see that in this table I have 4 different choices there. If you might notice that they're all powers of 2, and what this polymodulus degree exactly means, I'm not going to explain here. But if you look at our documentation, our examples, it's explained in great depth. But this scheme can be like kind of set up using multiple different parameterizations. A bigger polymodulus degree means that you have more computational capability on encrypted data. If you have a very small polymodulus degree, then you can do only small computations. If you have a big one, you can do more, like bigger computations. Now, for the rest of the columns, we have here encryption time, decryption time, addition of encrypted numbers, multiplication of encrypted numbers. But for each of them, we have the kind of latency of one operation and then amortized cost. This is very important because homomorphic encryption by nature is massively parallelizable. This means that, so this is kind of at like a very deep algorithmic level where this parallelism comes from. That's why it's important for us to say that, well, encrypting one number takes this and this long, and encrypting many numbers actually takes the same time. So the amortized cost is like thousands of times smaller than encrypting a single number. This is why it's important to think about what your computation exactly is. If your computation is highly parallelizable, then it can be a good match for homomorphic encryption. If it's completely non-parallelizable, then it's probably not a good match, and you might want to rethink how to structure your computation. And we have similar numbers for these operations. This is why sometimes it's difficult to say when people ask, okay, well, how long does it take? It's hard to say, because it depends on what your parameter set is, what your polymodulus degree is. You see that there's huge variation here. It depends on if your computation is parallelizable. So it depends on all these different aspects, how you implement your computation. This is why it's hard to answer exactly, how long does it take. So I actually wanted to show you some code, and before that, I'm just going to say a couple of words about the API. Seal itself is a very low-level library. It provides encryption, primitive operations on encrypted data, like encrypted addition, encrypted multiplication, and actually, like I said, it allows you to encrypt these. It allows you to do these SIMD operations natively. So you actually encrypt vectors of numbers, and it allows you to also rotate those vectors cyclically in encrypted form. And then, of course, it allows you to decrypt. With the code, we have many, many examples demonstrating this. And in the next release of Seal, which is coming very, very soon, we're going to have those examples even further improved and kind of made easier to digest. We have examples both in C# and in C++. Well, I'm just going to skip to showing the code example. We have, like I mentioned, two homomorphic encryption schemes, BFV and CKKS. Well, BFV is for encrypted modular arithmetic. CKKS is for encrypted real or complex number arithmetic. So they have different use cases. And I mentioned some of the objects that Seal uses there, but instead of talking about that, I'm just going to show you a little some of the code and create some very simple project using Seal.
And again, if you have any question at any point, raise your hand. Like, you don't have to wait for the end of the session. You can always come to our booth later, but you don't have to wait for the end of the session. Just raise your hand and ask whatever question you need. And let me know if you don't see it from the back. I don't think you will see it from the back, actually.
Oh. Well, unfortunately, these fonts are very small on the sides, but I can make the editor font easily bigger. Yeah. So I'm just... well, for those who at least who are in the front row, this is the, when you download the Seal source code, it has a Visual Studio solution file. It also has a CMake lists and all that good stuff, so that's going to help you build and install it very nicely on Linux and Mac OS. For Windows, for Visual Studio, using the solution file is obviously the way to go. Seal contains both the C++ part and C++ library, and then the .NET wrapper library, and examples for both. Here we have two folders in this, like two filter folders, native and .NET. And under native, we have the C++ library here. There's source files and there's header files. And this is basically the public API. So if you look at the header files here, that's what's going to be in the public API. We have examples, and we have unit tests. And in the .NET, we have kind of similar structure, although there's some C wrapper layer here that you first have to build, and then you can build the .NET wrapper library. Now, I've actually already built Seal here. Let me just make sure or you should build it in release mode. If you build it in debug mode, sometimes we have people do that, and then they report some incredible running times. And I'm like, well, it should run 10,000 times faster. So you're probably building it in debug mode. So make sure that you don't do that. Anyway, since Seal is already built, I just wanted to create a little demo example showing how to set this up, how to set up the encryption scheme, how to encrypt some data, some numbers, and how to do some computation. So here's just an empty, well, it's not so empty. There is one source file here, and some precompiled header, it seems. So the very first thing is I want to add seal/seal.h into the includes here. Well, of course, it's not going to find it because I haven't added it to the include directories. So let me do that. Additional include directories, solution, dir, seal, native src. All of this, if you download the seal source code, all of this is explained there. We're actually also working on creating some YouTube videos showing how to get this stuff set up and how to create some example projects. Solution dir, seal, native lib, platform, configure. All right. So now we added the library directory, and I built Seal as a static library in this case, but you can also build it, of course, as a dynamic library. So I have seal.lib here as a dependency, and well, if the gods of Visual Studio are smiling upon us, oh, well. Okay, I messed up something with my directories. Well, since the include directory is fine anyway, I don't care if my library directory is incorrect. I'm just not gonna build it. To get started, I will do using namespace seal, so I don't have to type seal everywhere all the time. Just gonna do that too. The very first thing you do in Seal, when you start using it, you set up encryption parameters. So this is a Seal object that kind of describes how the scheme is set up. Well, what scheme, you ask? Because like I said, Seal supports 2 encryption schemes. So we need to tell it that let's use the BFV scheme in this case. BFV allows you to do computation on integers modulo some number. Now, I need to set these parameters. So I'm going to set the polymodulus degree. This was one of the columns in the performance table. I'm just going to set it to 8192 for no particular reason. What these numbers exactly mean, again, you should look at the examples that come with the source code. There's like extensive explanation of how these affect performance, how these affect the computational capabilities, and so on. Then I need to set something called the coefficient modulus, which is a 3rd parameter. And let's see, default params, colon. I'm actually just gonna to set this maybe I'll make the font a bit bigger, make this full screen. To set this coefficient modulus, I'm actually going to use this function called default params coef modulus 128, and I'm going to give it the polymodulus degree as input, and this will give me a good value for the coef modulus. Some expert users might want to set the coef modulus to be some custom value. They might not want to use these default parameters, but for most users, at least who are starting to use this, using the BFV scheme, this default kind of coefficient modulus is a good choice. In the BFV scheme, I also need to set, finally, something called the plain modulus, and I'm just going to set this to 2 to the 32, for example. So, describing the scheme. After the encryption parameters have been set, I need to create a seal context object. So this is a context object like any context object. It contains information. It does pre-computations, and it validates that these parameters are okay. And the context object is used to create any other objects like encryptor, decryptor, evaluator. So I'm going to do... Sorry, where's Esther? What about the shift?
Where?
Probably you wanted to write the shift operator in the code.
Oh, I didn't? Well. Also, don't write 1 shift 32. That's undefined behavior. You don't want to do that. There's a lot of landmines there. Thanks, C++. So we can create a seal context in this way. And now, if you think of that client-server scenario, these encryption parameters are public information. So when the client and server communicate, when they want to do some encrypted computation, and one of them encrypts data, one of them computes on it, and then it's sent back, and you decrypt it again. Both of them have to know what these encryption parameters are. So these are completely public information, and both parties can create these seal contexts. So I'm just going to write here, both server and client can create this object. But now, the client wants to encrypt some numbers. So here's what they're going to do. They're going to need an encryptor. Actually, nope. Before doing anything, they need to set up keys, because we don't have any secret and public key. Homomorphic encryption is a public key system, so there's going to be a public key and a secret key. So I'm going to create a key generator, and to do that, I just give it the context. And from the key generator, I can now get the public key, and I can get the secret key. And of course, what the client would now do is it can give the public key to anyone, such as to the server or to its friends, and it keeps the secret key to itself. So this... all right. So it keeps the secret key to itself. And now it to encrypt some data, it needs an encryptor. Well, how do you create an encryptor? As with any object, you give it the seal context, but you also need to give it the public key. That's how public key cryptography works. To later decrypt, it can set up a decryptor, again with context, and it will need now the secret key, and you can set it up this way. We can create a simple plaintext. For example, let's encrypt the number 4. If you want to know why I'm writing a string there, you can come ask me. We can have a number 2 in another plaintext. And what we can do is we can create 2 ciphertexts, like that. And now what I'm going to do, I'm going to encrypt my 2 plaintexts. This is kind of very simple, because all you need to do is encryptor.encrypt, and you give it PT and CT1 as destination, and same for PT2, and CT2. Now, we have these 2 ciphertexts. You could actually serialize these. You could send them over to the server. The server can create an evaluator object, just like that. And the server can use the evaluator now to compute on this. So we can say, for example, the product of the 2 ciphertexts, the server can now compute easily by using evaluator.multiply CT1, CT2, and cprod. And now all the server needs to do is it needs to give back the C prod to the client, and the client can decrypt it using their decryptor, and they can get the plain text. And now, well, because I messed up my library directory, and because I'm out of time, I'm not actually going to run this program, and I'm not going to do the decryption right here. But decryption is just as simple as encryption. You create a decryptor, you do decryptor.decrypt, and it gives you out the plain text. So as you can see, we've actually put a lot of effort into making this API usable, and I'm hoping to actively engage with usability communities, trying to make it even better so that this doesn't have to be some really complicated mathematical encryption library. This can actually be relatively simple to use, and I hope that you give it a shot. Go to sealcrypto.org, go to our GitHub page, and try it. We have also some .NET demos available. There's links there. Thank you.